to learn Ethereum through this educational video series where we talk about EIP's upcoming features and important concepts. Here we are with one of the latest research topics, Verkle trees. Welcome to another episode of PEEPanEIP. I'm Pooja Ranjan, and with me we are William Schwab, my client. As per the proto-EIP of Verkle tree, it tries to solve a key problem standing on the way of Ethereum being stateless client-friendly. Its implementation will be the first step in a multi-phase transition to Ethereum exclusively relying on Verkle trees to store execution state. To talk about Verkle trees, we are joined by Dankrad Feist. Dankrad is a researcher at Ethereum Foundation and has documented multiple resources on the topic. Welcome, Dankrad. Thanks for joining us on the show.
Thank you, Pooja. Yes, so I'm going to give a presentation on Verkle trials today. I will try to keep it quite basic and understandable, but I'm going to link to all the further resources if you want to go into the cryptography and the math or yeah. Before
you go ahead with the topic, I'm super excited to see what you have got to share with us. It would be interesting to know a little bit about yourself. So can you please briefly introduce yourself and let us know how you joined the Ethereum research group?
Yeah, sure. So I am Dankrad Feist. I work for the ETH2 research team. I joined the research team in early 2019. Yeah, that was after having worked with some of them on some small problems for a few months beforehand. And yeah, I mean, since then I've been working on everything, like mostly things that concern ETH2, the proof of custody, the data availability checks, and other things. So this was kind of the first time earlier this year that I started with a discussion with Guillaume from the Geth research team that I came to the conclusion that I should try to see if Verkle tries would help with ETH1 state. And yeah, we came to the conclusion that we believe that they would be much better than what we had so far. So that's how I came into this and started working on this for a part of my time.
Thank you so much.
Cool. So for my presentation, I will start with presenting the problem. So we'll go through the definition of weak statelessness, which is what we're aiming for now, and what the problem is that we have with current commitment schemes, i.e. Merkle trees or hexary Merkle trees as they're currently used in Ethereum. I will show how Verkle tries work, and then I will also go into how we actually are currently planning to use Verkle tries to commit to the current Ethereum state. Earlier this year, I wrote a blog post about this, where I presented the case why we really do want statelessness first, but that the best paradigm is weak statelessness. And the idea behind this is that the state is not required to be a fully validating node. That's the definition of statelessness. So for example, ETH2 validators will not need the state, which will be a huge burden removed from them and will enable things like staking from Raspberry Pis or mobile phones and all that kind of really nice stuff. But also, as a very important point, is that statelessness will actually allow fraud-proof protected light clients, as in light clients that don't just verify the consensus, but can also easily receive a fraud proof in case the consensus that they receive is actually invalid. It's to some to a chain that contains an irregular state transition, and in that case they should not follow it. And this is so far not possible, but it will actually be easily possible once we have statelessness, because every block in itself is simply valid or not. You do not need any other information to validate whether a block contains a valid state transition, and so the block itself is a fraud proof, which is basically I would say, the most elegant solution to this problem. What weak means is that block builders / proposers. So I mean, I'm doing this like either or here. Well, we don't know yet exactly how the future is going to look like, but someone has to compose a block, like basically batch transactions together and compute the new state root, and whoever that is will actually still need the state. And we basically say it is fine, like, to have these higher requirements for quite a few reasons. One of them is that very likely this role will anyway go to people who are more involved in extracting MEV and so on. So it seems like right now that everything is going to that direction anyway. But also from a practical perspective, it's actually not that bad, because it is still roughly what an Ethereum full node needs now. So like, we're not going crazy here. It's not going to be like suddenly you need a huge computer to do this, that you can only get in a data center. It's just slightly more than what you need to run a normal full node that does not have all the state. Of course, you need enough space to store state. And one of the nice things that this also solves is that the huge discussion we had last year around the dynamic state access is not going to be a problem, because the one who composes the blocks actually has the full state. So the problem with achieving the statelessness is that currently, so Ethereum does already commit to the full state using hexary Merkle trees. But if we just try to add all the witnesses to a block, I'll come to the computation of these numbers later. Actually, it's a little bit worse right now, but we're going to change it with an EIP. With hexary Merkle trees would be up to 47 megabytes using currently the max 30 million gas block. That is huge. Like that would be a massive problem. If we did just switch to a simple binary Merkle tree, which is basically the best possible alternative we had previously, would still be 8 megabytes. Yeah, it's still pretty big. So it's not very practical to do either of these. So I will come to present my the solution that I suggest here, and let's first start with decomposing this word Verkle trie. There's a lot in these two words, and I just want to make it very clear because it's very confusing and like feels like completely random, but it's not. So Verkle is simply a composition of the two words, the Merkle tree, but with a vector commitment instead of hashes. So that's where the V comes from. That's the only thing that's changed about it. So it's basically a tree that works similar to Merkle trees, but the commitments will be vector commitments instead of hashes. And I will come very soon to what a vector commitment is. And a trie is actually simply a special kind of tree. It's a composition of the words tree and retrieval, and it's basically just each node in the tree represents a prefix of keys. So don't be confused if we're talking about tries. That's just a technical term. You can just think of a tree, but it's used to store key value pairs. Okay. So to illustrate how this works, I've drawn here a Merkle tree that commits to 16 leaves. At the bottom, you see the leaves with index. I made them binary indices, and because that's much more clear in a Merkle tree. And the idea is always each node is simply the hash of the two child nodes. So it's a binary Merkle tree. So this inner node 0 will be the hash of inner 00 and inner 01, and analogous for all the other nodes in this Merkle tree. And the cool thing about Merkle trees is that we can compute Merkle proofs. So let's say we have this leaf 0110, and we want to prove that this is part of this Merkle tree. then what we have to do is simply enable the verifier to compute all the hashes on the path. And that's quite easy. We just always give the sibling. So if we give this direct sibling of our green leaf that we want to prove, that's 0, 1, 1, 1, then we can compute the inner node 0, 1, 1. And now we add another sibling, inner 0, 1, 0. And together with these two, we can again compute the inner node 0, 1. And so on until we arrive at the root. So in the whole process, we only had to give 4 additional hashes, the 4 siblings of the nodes on the path, basically. And that allows us to compute this complete proof that this leaf is part of this Merkle tree. So now what happens if we change the width of a Merkle tree? So to illustrate, I've drawn here a Merkle tree of width 4 instead of the 2 previously. So as before, each node is the hash of all the children. So now it's always 4 children. So let's see what happens if we want to compute a proof. So we have this leaf 0, 1, 1, 0 that we want to prove as part of this Merkle tree. We have to give all of its siblings, because only if you give all the siblings can you compute the hash that's part of node inner 0, 1. So I need to give all these 3 siblings of the green leaf. And then again, I have to give all the 3 siblings of node inner 0, 1 in order to compute the root. And now you see where the problem is. We have increased the width. Previously, we needed 4. We have the same number of leaves, right? It's still 16 leaves, but instead of having to provide 4 hashes in order to give the proof, we suddenly now have to provide 6. So it actually becomes strictly worse. So this is annoying, basically. If you increase the width, then you need more. You have a longer proof, and this is exactly what happened in Ethereum, because it was chosen to have hexary trees, which is width 16. So the proofs are actually very, very big for that reason, which is very unfortunate. So yeah, this is a summary of that. The problem is you need all the siblings. So now we can ask the question, what if we had a scheme where we could prove this membership more efficiently than by providing all the siblings? So to get rid of this problem here, the problem is really you have to provide all these siblings. That makes it very large. And this is where vector commitments come in. So we have some vector, think of x1, x2, and so on as some sort of values, say probably each 32-byte value is a very typical thing. You can compute a commitment C to all of these values, and an opening is a proof that some xi for a certain index has a certain value. So this opening will be another binary string of some sort, and with the property that when I as a verifier receive this opening, I know that xi equals v. So this v has been provided by the prover, and as well as this opening, and together they give a conclusive mathematical proof, essentially a cryptographic proof that this was correct. So in this definition, we did not say anything about the size. So actually a Merkle tree itself is a vector commitment. A Merkle tree has this property. We did earlier see we could commit to a vector of length 16 in our case, and we could compute a proof that a certain index had a certain value, and the proof size was the log2 of n, where n is the length of the vector. So a Merkle tree is a vector commitment, but of course, what we're actually interested in are more efficient vector commitments. So Verkle trees will only be interesting if we can somehow find a more efficient vector commitment. One example I'm going to give here is that I have also give some presentation in the past. So if you want to look it up, I introduced this before. I also wrote a blog post about it, but it's actually a polynomial commitment that's much more powerful than just a vector commitment, but you can use it as a vector commitment as well. And just the properties are that the commitment will be one group element. So if we, for example, use BLS 12381, which is the curve we're going to use in ETH2 for most things, then it will be 48 bytes to compute a commitment. So that's slightly larger than a hash, but not much. And the proof size, like if you reveal any element of that vector, is also going to be 48 bytes. And now this is interesting because it doesn't matter how many elements the vector has. This proof always stays the same. And it doesn't matter whether it's 2, 100, or 10,000 elements in the vector. And this is a good model to have in mind for vector commitments. Like this would be like the ideal thing that we would want to have, as like we have like a constant size for the commitment and also the proof size is constant. It's not actually what we're going to use for Verkle trees, but it's a good idea to probably read about this first because it's a very nice example. So now what happens if we change it, this width for Merkle tree to a Verkle tree? So now instead, like, well, so far we've just changed that each node will be this vector commitment of the child nodes. Now, the interesting thing is what happens when we open this. So again, we want to open this leaf. We have to provide this inner node and the opening. So this is open of 3. I just wrote the index, and in reality, there are more things you need to compute this opening than just the index. You always need the full vector as well. But it's basically the verifier will only see this opening. Then they can verify, aha, this leaf is part of this node. And then they have another opening that will show that this node is part of the root. By the way, one slightly thing that's a bit different than compared to Merkle trees is that this opening itself will not be enough to just compute the inner node. So in the Merkle proof, once you have the siblings, they are actually sufficient to just completely compute the node, and you don't need to provide the node itself. This is not the case anymore. So this changes a bit. You actually have to provide the inner nodes themselves, but you don't have to provide the siblings anymore. You just provide the openings. Okay, so now we are down to 3 elements. Actually, in almost all cases that we're interested in, the commitments will be additive. And that means that you can do certain things with the commitments and the proofs, which are very nice. What happens is that all the openings can be compressed together in a single one. So actually, like you might think, oh, we need all these inner nodes plus all the openings, but all the openings will be compressed into a single one. So that's really nice. And so actually the real size of the proof is only determined by all the inner nodes. Like the openings will always be a very trivial part of it. Yeah, so that's illustrated here. So there's basically the inner node and then the opening for everything. And just a quick illustration to also come to the trie part of the Verkle trie. So that's basically a trie means that that whenever you go down in the tree, you basically follow a prefix of the key. So here on the left, you see all the keys that start with the prefix 00. So they will be summarized in an inner node that's about 00. And so that inner node contains everything that has the prefix 00. And so that's a very nice way to store key value pairs, which is the main thing we need to do for the Ethereum state. Cool. So yeah, that's roughly the idea behind Verkle trees. So the idea is only like the only thing you have to remember, it's about combining a vector commitment with a Merkle tree. That's what a Verkle tree is. I'm now going to become a little bit more concrete. I'm going to talk about what we actually want to do for ETH1 state, and the vector commitment we want to use is called the Pedersen commitment. You might have come across it before. It's very popular for inside snarks, for example, because it's very efficient to verify, much more efficient than hashes. It has some slight disadvantages compared to the KZG commitments when you want to open only a single one. To open a Pedersen commitment, you need something that's called an inner product argument. This part I will not go into details about. I can refer you to some resources if you want to read about it. I'll also have a link later, but I will explain what a Pedersen commitment is. The advantages why we want to use this is that we don't need pairing-friendly groups, and pairing-friendly groups that are the main reason why we have such large group elements. For example, for BLS 12381, it's 48 bytes, but actually, if you don't need pairings, then you can use smaller groups, and they only need 32 bytes. You don't need a trusted setup, which is really nice, and I think is a great advantage if you're dealing with something as delicate as state, where you really want to be sure that that everything is sound. Another great advantage is that if you do it in a curve that's well aligned with your curve, basically if it fits into another curve where you can do snarks, then you can do everything very efficiently inside a snark, whereas that's not the case for hash functions. Like computing a SHA-256 hash in a snark is a huge effort. It's very, very difficult, costs tens of thousands of constraints typically, so that you don't want to do that. But Pedersen commitments with a curve that fits inside BLS 12381 in our case is very efficient. So this makes this future-proof. So in the future, once that becomes efficient enough, we can basically add witness compression, where we further compress down our witnesses to a much, much smaller size and make them very efficient to verify. Actually, potentially we can do that now. It just has a bit more latency. Like it might take maybe like a few minutes or hours until this can be added. But yeah, so that it's probably possible now, to be honest. And it also enables use of these in ZK rollups. The only disadvantage of this is that compared to KZG commitments, it's not as efficient if you just want to prove a single witness. But this is a very, very rare case. Like I don't think, yeah. I mean, even a transaction proof would at least use four openings, and already then it's like not really much worse than KZG commitments. Cool. So how do Pedersen commitments work? We have some elliptic curve G, and we have some generators G1, G2 up to Gn. So that's the length of the number of these generators has to be the same as the length of the vector that you want to commit to. And the important thing is that you want that the relative discrete logarithm between these generators is not known. So nobody should know this Q, so that G1 equals Q times G2. Like we know that it exists, but nobody should know it. And the nice thing is you don't need a trusted setup in order to do that. You just need a sort of hash that generates these, and this can all be done in public. You don't need to trust anyone. And if you want to commit to a vector, x1, x2, and so on, of field elements, then you simply multiply each of them by their respective generator and take the sum. So it's C equals x1 times G1 plus x2 times G2, and so on. So very elegant and very simple. And yeah, here's my a link to my blog post if you want to read about how to open these using inner product arguments. Yeah, so now this is basically starting to compare, like how good can we get with these Verkle trees. So this is based on this 32 byte group elements. And so with the same comparison I had earlier, here I have the numbers as well. So this was based on the new proposed gas cost per state axis of 1,900. The current gas limit is 30 EM for like completely full EIP 1559 blocks. So we have about 15,000 state axes. So unfortunately, with hexary Merkle trees at the moment, that would generate 47 megabytes of witnesses in the worst case. So these are all like worst case number. Binary Merkle trees are 8 megabytes, and if we use with 256 Verkle trees, then we can get that down to 1.5 megabytes, which is a manageable number for like the absolute worst case block. So this is a block that literally only accesses random elements of the state. So in practice, they're going to be much better. We're talking about a couple of 100 kilobytes. Yeah, so quickly to talk about, I'm actually not going to go into the math here, but I wanted to reference these. I wrote a blog post about these as well. So if you want to know how to open all these commitments and combine them, then read this blog post. There's all the math is in there. But this is the part where we need this weak statelessness. So like basically, in order to compute, to combine all the proofs, you need someone who has access to the full state. Cool. So one question that I haven't gone into is about the cost in terms of computation. So far we've only talked about witness sizes. This is the major reason why we really want Verkle trees. There would be other polynomial commitments, as you know, like for example, KCG commitments can get all witnesses down to constant size if we wanted to. However, their problem is that the computation is insane and unfortunately not manageable. So I'm going a bit into the costs. So all these numbers here are projections from, I know that we can get the basic operations down to these numbers, but current implementations are not there yet. So see these as projections rather than benchmarks of what we have implemented right now. So there are two kinds of operations. There are field operations, which basically always refers to additions and multiplications in prime fields. Well, the interesting part is multiplications. Additions are pretty much trivial. And the multiplication cost in a prime field of size about 32 bytes is about 30 nanoseconds on like modern hardware. The other type of operations we have are group operations. These are additions and scalar multiplications in an elliptic curve. And specifically, we are talking about Bender's net. This is a highly optimized elliptic curve where you have a GLV endomorphism so that some things are a bit faster. A plane scalar multiplication costs about 40 microseconds. So this is always like, so you got to be really careful with these numbers because there's a factor of 1,000 between these, right? Like confusing microseconds and nanoseconds is really not acceptable. It's a huge difference. So whenever we can, like field operations are basically extremely insanely cheap and group operations are a lot more expensive. The good thing is that in many cases we can reduce these. So there are so-called fixed base multiplications where if you already know beforehand what your base is going to be. So for example, for Pedersen commitments, we have these generators G1, G2, so we already know them. So if we know that we're going to do a lot of multiplications with them, we can do a pre-compute and then we can get that down to about 5 microseconds. And the other thing is we can do multiscalar multiplications if we have like a lot, like a linear combination of a lot of scalars and a lot of group elements, then we can also accelerate it and it actually becomes faster not as time increases, but as the number of elements increases. So that's also really nice. And as a comparison, like a very rough ballpark, like a hash costs about 1 microsecond or so to compute. Okay, so let's talk about the cost in practice. So the prover, the main operation that they need to do is per opening. So for each vector commitment opening, they will need to do about 4 times 256. So 256 is the width. So for each sibling, essentially, they have to do about 4 field operations. But operations actually mean multiplications here. So that's about 30 microseconds. So each of them is 30 nanoseconds and then times 1000. So for 5,000 proofs, which will involve opening about 25,000 vector commitments, because for each proof you need to like go through the whole tree, right? So we're at about 25,000 openings. That would be 750 milliseconds. So that's a fairly acceptable cost that only the prover needs to do once for every block. So like it doesn't really set a huge barrier in order to become a block producer. The verifier, the main cost in the multiproof scheme is multiscalar multiplication, and the size of that will be determined by the number of commitments that have to be opened. So that's the nice thing. This is less the number of openings. So basically, maybe we go back to the Verkle proof, right? So here I'm opening 2 commitments, inner 01 and the root. For each, I have to open these 2. But let's say I also wanted to prove the leaf 0100. That's actually a sibling of 0110. This is another opening. So I have to open this commitment inner 01 now at 2 places, but it does not open a new commitment. And this, the marginal cost for this is very, very low. So that's nice. So that's why it's less. Like I estimate here roughly like 15,000 commitments that you need to open. So the multiscalar multiplication would be of size 15,000. This number is the one I'm least certain about. I estimate that once we have well optimized implementations for this could be in the range of 50 to 150 milliseconds. And a very nice thing here is the marginal cost of opening another position in the same commitment is like super low. We're talking about nanoseconds, really, like actually less than a hash potentially. So that's where we come to the tree structure that we are suggesting now. So the idea is that what we want in our design goals is that we want to make access to neighboring code chunks and storage slots very cheap. So like when a contract is executed, you expect that much of the code that you access is like actually very close to each other. So you want that not each of these represents a random state access. So we want to make that cheap, but we have a kind of conflicting goal that it would be nice to distribute all the state as evenly as possible in the tree, because then stuff like state sync becomes much easier. You can do it just by like prefixes and stuff. So that would be nice as well. Further, we want that the scheme is fast in plain text. So we want that opening neighboring chunks not to involve opening a new commitment. And we want it to be fast in snags. And that mainly means we want no hashing. We only want Pedersen commitments because they are fast. And the last design goal is it should also be forward compatible, because we expect that in 5 to 10 years or sometime, we want to upgrade to a post-quantum scheme, and then we should only, we only want to work with a pure key value store and not do something complicated due to the scheme that we're using now that then won't map to the new scheme that will have to upgrade in the future. So in order to achieve this, we basically do something with the key. And the idea is this: I'll only talk about storage. Everything else is kind of similar, but this gives you the idea of how this is going to work. So we have a contract address and a storage location that we want to access. Each of these are basically 32 bytes. What we compute is what I call the stem. And that is a Pedersen commitment of this contract address and the storage location minus the last byte. So we don't include the last bytes in the storage location. Think of this Pedersen commitment just as a hash function. The reason why we're doing Pedersen here is once again so that in the future snarks can do this also very efficiently, but ignore that and think of it as a hash if that's easier for you. And then this last byte of the storage location, I'm using Python notation here, this -1 is the last byte. We call the suffix. And so that's not included in the stem. So the very last byte does not change the stem and it just passes straight through into the suffix. And so that gives you this idea that what I said earlier, we want that very close storage location, which basically means most of the time that the suffix will be the same, will map close to each other. And so the way we do that is they only change the last byte. And then this is how we compute the tree for this. So basically the stem will feed into a Verkle trie, pure Verkle trie structure. And then for the suffix, we compute the so-called suffix tree. So basically once the Verkle trie will go up to a position where there's no other stem with the same initial. And at that point, there's this extension node that is a Pedersen commitment to one stem and two commitments. The one here is to distinguish it from any other node because all nodes are Pedersen commitments. So we need a clear marker here that something is not an inner node, but this extension node. It will commit to two different nodes that will then directly commit to the value. So, and value lower and value upper are each 16 bytes of the value. So the value is 32 bytes. The reason why we're splitting it in two is that we cannot store a full 32 bytes directly in a commitment because the field is a bit too small for that. And so to make it unique, we have to split it up in two of 16 bytes each. And that's also why we need these two commitments here in the extension node, because each of them can only store 128 bytes, but we have a total of 256 bytes that have the same 256 values that have the same stem and have to go into the same suffix tree. And yeah, here you can, this is a link below to the current Verkle Trie EIP written by Vitalik and me that implements this. Cool. So yeah, to summarize, the main advantage of Verkle trees is it's a huge reduction in the witness sizes. So we're talking about 5 times versus the binary Merkle trees, which is so far the best alternative we know of, and more than 30 times compared to hexarity. So that's, yeah, that's huge. We need to change definitely, and hexarities are just terrible. The verification times are actually in the same order of magnitude, same range as binary Merkle trees. Prover overhead isn't huge. We're talking about a few seconds in the worst case and can run a normal machine. Doesn't require a trusted setup. And currently, as far as I'm aware, it's the only solution for Ethereum state that doesn't come with huge trade-offs of either making witnesses huge or imposing a huge prover that can't be run on a normal machine. All right. Yeah, thank you. This is the end of my presentation. So I think it's now time for questions.
Thank you so much for presentation. Yeah, I see we have some questions in the chat. Lightland, if you would like to go ahead with that.
those are awesome slides, by the way. I really like the graphics in there. My first question was, can you talk a little bit about why you need a Verkle trie in the first place? Why can't you just have one flat level commitment of the entire state?
Mm-hmm. Yeah, so that's an excellent question. So yes, so obviously, like when you go back to the vector commitment, like it says like you can give the proof for any element with just this constant size, right? Well, at least for certain commitments like KZG. The problem is that for all vector commitments we know, and we actually now think that's a fundamental property, if the proof is constant size, it means you need to do something to compute the proof itself. You need to do something that involves everything that's in the vector commitment, right? So like say you take a KZG commitment of the full state, which has like 1 billion elements, then computing the proof needs to do something with those 1 billion elements. And yeah, you can see that doesn't scale, like it doesn't work. So it's actually, it's purely about the prover. If we only talking about the verifier, this is clearly the ideal. And actually like the width of the Verkle tree is a trade-off between prover work and verifier work. And
interesting.
Yeah. And so like basically this is a concession to the prover that we don't want a huge and extremely inefficient prover.
So this kind of alludes to my second question. What data do you need to recalculate the root of the Verkle trie? Can you only recalculate it with the updated leaf values and the branch nodes, or do you start needing to access all leaf nodes?
Oh, updating. No, like if you have a state access, basically you need, yeah, so like you need to, you can update it in a similar way to a Merkle tree. So you need all the intermediate commitments that go to your leaf that you've changed, updated, and then you can compute the update from there. So essentially, a Verkle proof also gives you all the information to update the root for that leaf. Yeah.
Okay, I see.
Yeah, so that's very nice, and that's also essential for statelessness, because you obviously need to be able to update the root for statelessness.
I have a question related to state expiry. So what is the basic difference between account level versus the storage slot level expiry?
So I'm not super familiar with state expiry, but I mean, I think like account level would be that whole accounts expire, and storage slot would be that each storage slot itself like has to can expire and has to be reinstated. I'm not aware that there is an account level state expiry proposal. Maybe there is. But I think like what we are suggesting is would be that each slot itself can expire. Yeah.
Yeah. Thank you. So I came across this another term related to commitments. It's about the bulletproof commitment and the Kate commitment. So why the Kate commitment was preferred for the Verkle tree?
No, actually, oh no. So we originally started with Kate commitments. So KZG or Kate commitments. I introduced them earlier, but we have now pivoted towards Pedersen, which is bulletproof, essentially. Like that's just another name, yeah. So we are using bulletproof commitments because we have figured out that they are pretty much better in every way for our application specifically.
Right, thank you.
There was some mention about setting storage slots to 0 explicitly instead of deleting them. Do you know if that has to do with Verkle trees in particular, or more related to expiry stuff?
That is related to expiry, because basically, if you want to expire a state, you need to be able to tell whether a slot has existed and been written to 0 or has never existed. Like basically, because you need to know whether this slot is part of the current state or whether you need to look up some old state. And if you just deleted it in the current state, then you would lose that information. Yeah. So we need an explicit distinction between has never existed in a state and has been deleted or set to 0, which is the same thing.
Great, thanks. Also, I really appreciated having the source in the Verkle Trie write-up, like understanding the verifier that way was really helpful. If there's any way to add the source for proving a commit, or for verifying rather, that would be like helpful as well. I see the source for like proving the commitment, but I didn't find the source for verifying it.
What do you mean by source?
Well, in the Verkle Trie, there was like Python code, and yeah, like showing how to generate the root and all that, and that was, it's sort of the most complete way to sort of understand it, I think.
Cool. Could you clarify where you're looking at, where you find that?
Yeah, it was just on a slide you had a moment ago. It was like it was under Vitalik's Verkle Trie on notes.ethereum.
I see. Yeah. Well, so Vitalik, the EEP doesn't focus on actual witnesses or anything, right? The EEP is only about defining it, because everything else can be kind of derived from there. So, but I think I would hope my blog post. So here, this one. If you look at this one, the details, PCS multiproofs blog post, that should have all the details on how to both compute an opening proof and verify it.
Okay, thank you.
So we have got this one question from our Reddit user. It seems like this question was already asked somewhere else, but he's curious to have your perspective on that. So, how feasible is it to verify a vector commitment inside an EVM transaction?
Good question. So we'll need to add opcodes for whatever curve we are using. I think the only sensible thing is to have that native in the VM, because we are going to every client needs to have it anyway. So why not also add it as an opcode? I think then it would be very easy to verify it. Once you have the basic curve operations, without them, I don't know. I suspect it's actually possible now to implement this, because the math is not that bad. Like the group is a very nice small group. You could probably implement it. It would be a bit gas inefficient probably. Yeah, but probably doable. I'm not really an expert in implementing cryptography in smart contracts, but I feel like it should be possible.
Thank you. So my next question is related to the process and the timeline. I know there have been research on this Verkle Trie for a while. So, and there is also a proto-EIP app that Vitalik shared the other day. When do you think we can have a formal proposal, like it is still not as in pull request for the Verkle trees, and like when it will be ready for client to start discussing for inclusion in future upgrade?
Yeah, I probably don't want to give a firm timeline here, because I haven't discussed this with everyone. So there's a team. So the Guillaume Ballet from Geth is currently working on this. I'd say there has been a bit of disruption of timelines, because we have done some major changes in terms of pivoting from KZG to Pedersen commitments, for example, as we just discussed. So I think we kind of have to go through that again and see where we land. I don't have really good estimates on the timelines right now. But there is a team already on it implementing it of about 5 people or so. So I expect that hopefully in the next few months, by the end of the year, we should have good prototypes, and we should have enough to put that into an EIP very roughly.
Right. So when you mentioned by the end of the year, is it fair to expect that this would be something which will be considered after the merge?
Yes, for sure. Yeah, no, I mean, we're definitely not going to do that before the merge. I mean, ideally, of course, like I'm very adamant that like statelessness is very central, and like I would really like to have it as soon as possible after the merge. But of course, that depends on all the implementation and everything. So I can't really say what the constraints there are.
Interesting. Yeah, we are getting close to an hour. So yeah, if anyone else has any question for Dankrad or on this proposal.
I just had a like more general question. Like, what are the risks do you see of the transition to the Verkle trie? And specifically, one question is like, how new are these crypto primitives that the Verkle trie require, and are they things that we think are time tested enough to be used at the base protocol?
So the good thing is that what we're considering now is really only dependent, like Pedersen commitments only depend on a discrete logarithm assumption, which is, I would say, very time tested. Like, I mean, that's basically like Schnorr signatures, which we use all the time. Like, so it's very basic. That's nice. We are suggesting a new curve. I talked to cryptographers and they said that like our methods of generating new curves are very reliable, and like there's no like I would definitely want to have it vetted more, but from cryptographers I've talked to, they didn't tell me that there's any concern about that. So I would say I don't think cryptographically there are major concerns anyway. I think, but I think there is definitely some complexity, for example, in the multiproof. So I guess that would need yeah, quite a bit of work to be really sure, and auditing. Yeah, but I would say not on the basics. Like the basic assumptions are very sound.
Do you think there's any possibility that there's too much reliance on the underlying structure of Ethereum right now, and we may get to a point where we're seriously trying to make the trie upgrade to Verkle trie, and there are different communities who say this just can't be done because we made these assumptions on this, and then,
right? I don't know. Is that like, I mean, are you aware of any smart contracts that are trying to verify state on chain now?
there's definitely some smart contracts that verify like Merkle Patricia witnesses. And I don't know for sure, but I heard some people talking about some bridges on other chains that do have logic that relies on
right,
verifying witnesses. And so again, like I think this is going to be a really tricky thing. I think at the end of the day, we'll be able to upgrade, but it is going to be a hard thing to convince everyone, and probably needs a lot of lead time to ensure that everything is upgraded.
Yeah. I mean, my expectation is that for most of these projects, their bridges to Ethereum are probably so central that they will just upgrade them and do whatever hard fork they need. So the only real danger I see is any smart contract that does state verification. I'm not sure why anyone would do that, but yeah. Yeah, I don't quite understand the use case for verifying state via the commitment on Ethereum itself. But yeah, definitely something to look into. Yeah.
Any other risk classes you might see, or generally like kind of just those two?
I mean, there's the question is, are we going to just discover better commitments while we're doing this? And we're like, oh shit, like we should have used that. I think it seems very unlikely at this point. Like we are investing in it, but I haven't seen anything on the horizon at the moment that looks like it's actually even close to being competitive. Yeah.
is 1.5 megabytes for the witness acceptable for 15-second block times? Like,
so just to be clear, this is the absolute max.
Sure.
Right. This is and I mean, I think that's if you can just fill a block with call data. I mean, that's also going to be what 2 megabytes by now.
Yeah, that's true.
So I feel like it should be, but yeah, I mean, definitely things to think about. Yeah, you also have to think about all the edge cases here, which are of course like what you like, how you can exploit the lower cost for accessing data in the same suffix and stuff like that. I have done some comparisons, like I've got some sheets and try to go through it. The thing is, of course, all of this currently, as I said, they aren't benchmarks. They're basically my estimates on like what all the basic operations cost. To that, you generally have to add like all the database operations potentially. That has to be really well optimized. Like there's not a lot of slack on that. I think it can be, but that's definitely a hard problem. And then there's all the potential like bottlenecks in the hardware of streaming all that stuff through. I don't know. Yeah, definitely all of these numbers are going to get a bit worse. The question is how much worse.
Cool, thanks.
Thank you. I appreciate you joining us, Dankrad, talking about the concept of Verkle Trie and how we can see that being implemented maybe on Ethereum blockchain in upcoming days. Hoping to have you again on the show to talk more on the progress when we have like formally documented EIP once again. Do you have any final words for our viewers where they can follow you and follow the research work on this Verkle Trie?
Oh, where they can follow? Yeah, so that's a very good question. I think like, I mean, I try to write things down regularly. Yeah, like follow us on Twitter, I guess, where I would usually post if there's some new proposal or a new post about something. That would be my suggestion.
Nice. On this note, for all our YouTube viewers, thanks for watching. And if you like it, please share it with people of similar interest. And of course, we are going to add the Twitter handle of the guest and the presentation, plus the resources that he has documented in this slide. And we have collected it from the internet. I'll be looking forward to all your feedback, improvement suggestions on the series and the topic that you would be interested to learn. Reach us on the Ethereum Cat Herders Discord. Details are provided in the description box. In the upcoming episodes, we'll be talking about Altair, the next upgrade Ethereum chain will be witnessing. So stay tuned, keep watching, keep sharing your love with Ethereum Cat Herders. See you all in the next episode of PEEPanEIP.